Welcome to the Copperfield Electric Podcast. If you just swap a 20-amp breaker for a 30-amp breaker just to stop your high-end hairdryer from tripping the power in the morning, you haven't actually fixed the problem at all,
Oh, not even close. You've actually just removed the only safety valve that's preventing an electrical fire from igniting right inside your drywall.
which is a terrifying thought. So today we are doing a deep dive to completely demystify that flat, gray, honestly intimidating metal box stuck to the wall in your garage or your basement.
It really is an interesting phenomenon. I mean, people treat a tripped breaker as this massive electrical failure, when in reality, it's a mechanical success.
Right, because it means the system actually worked.
Exactly. That click into the dark means the safety system engineered into your home did exactly what it was designed to do. But approaching that panel to reset it, or even just to evaluate your home's capacity, it requires a very specific operational baseline.
And that is exactly our mission today. We are using technical guides and field resources provided by Copperfield Electric. They are a top-rated 24-hour electrician service out in Orange County.
Yeah, they really know their stuff.
They absolutely do. And today we're looking at the exact mechanics of reading your home's electrical panels safely. Whether you are prepping for, like, a new EV charger, dealing with a persistent thermal trip, or you just are insanely curious about how your own property works, this deep dive is going to make you a much more informed homeowner.
Absolutely. And before we even look at the bus bars and the breakers inside, we really have to establish the physical rules of engagement.
Yeah, the absolute hard line on physical safety, which starts with moisture. Opening the panel is like popping the hood of a car,
Yep.
You can safely check the oil, but you don't start unscrewing the engine block while it's running.
That is a perfect way to look at it. And the human skin is naturally a pretty good insulator when it is completely dry. Like the outer epidermis has a high electrical resistance.
Measured in ohms, right?
Right, exactly. But the moment you introduce water, whether your hands are damp from washing dishes or you're standing in a slight puddle down in the basement, that resistance just plummets.
Oh, wow, so it's immediate.
Oh, yeah. Water bridges those microscopic gaps in your skin, turning your body into a highly efficient, low-impedance path straight to the ground. You never touch the latch on a panel door unless your hands and feet are bone dry.
I mean, that makes total sense. Now, the Copperfield Electric Field Guides highlight another physical rule that I found incredibly specific. They mandate that you should always stand slightly to the side when opening the panel door.
Yes, using your arm to reach over.
Right. You never stand dead center, squared up with the box. But my instinct is always to stand directly in front of the thing I'm opening to get a clear look. Why is standing to the side so important?
What's fascinating here is that this positioning isn't just about general caution. It is an active defense against the physics of an arc flash.
An arc flash.
Yeah.
That sounds intense.
It is. An arc flash isn't just a simple spark. If a catastrophic short circuit happens exactly as you pull that door open, say a main lug has vibrated loose over a few decades, the resulting energy violently superheats the surrounding air.
Just instantly.
Instantly, that air ionizes and literally turns into a conductive plasma channel, expanding outward like a shockwave. So, by standing to the side, you are taking advantage of a free physical insurance policy.
Oh, because the door's in the way.
Exactly. You're using the heavy steel panel door as a temporary blast shield, which keeps your face and your torso out of the direct path of that thermal expansion.
Wow. Okay. Note to self, always stand to the side. So once you swing that door open safely, you're confronted with the breakers. But those switches are seated in this large metal cover plate that hides all the underlying architecture.
Right. The industry terminology for that plate is the dead front.
The dead front, got it. And it's an engineered physical barrier between you and the live, uninsulated metal parts behind it, right?
It is. And the rule here is absolute. The homeowner never, under any circumstances, unscrews that dead front to look behind it.
Because that's where the real danger is.
Exactly. The moment you remove the dead front, you are exposing the main utility service cables. Those lines come straight from the utility pole or the underground transformer.
So they don't have a breaker of their own to trip if something goes wrong.
No, they do not have secondary overcurrent protection on your side of the meter. They are live, incredibly powerful, and highly unforgiving. The dead front remains in place. Period.
Makes sense. Now, while you are observing the panel, you also have to use your senses to detect mechanical red flags. Like if you see distinct scorch marks on the plastic breaker casings or hear a low, continuous buzzing sound.
The buzzing is never a good sign.
Yeah. Or if you smell ozone, which has that sharp, almost metallic, burning plastic scent. If you notice any of that, you close the door and stop immediately.
Right, because ozone is a byproduct of corona discharge. It means electricity is literally ionizing the oxygen in the air inside your panel.
And I'm guessing you definitely don't try to troubleshoot that yourself.
Never. You step away and call a professional. Those sensory clues are the physical symptoms of a failing connection that is rapidly generating heat. Touching the panel to investigate further risks, disturbing a connection that is already on the verge of critical failure.
Okay, let's assume the panel is quiet, cool, and smells fine. We are safely standing to the side. Let's map the architecture. The whole system is basically identical to a home's plumbing network, right?
Yeah, that's a great analogy.
So the main electrical drop from the utility is your high-pressure water main. And the main breaker, which is usually that massive switch isolated at the very top, is your main water shutoff valve.
Exactly. It governs the entire downstream system. The number printed in bold on that main breaker, usually 100 or 200, represents your home's total service size in amps.
And that tells you your maximum capacity.
Yeah. Right. It dictates the maximum volume of electrical current the combined panel can pull from the grid at any instantaneous moment. A 100 amp service was standard decades ago, but a 200 amp service is really the baseline for modern infrastructure.
Because we have so much more running now. Central air, multiple appliances, EV chargers.
Exactly. We draw a lot more power today.
Okay, let's unpack this. Below that main shutoff, you have the two vertical columns of branch circuit breakers. These are basically the individual pipes routing power to specific zones.
Yep, the branch circuits.
And the single pole breakers, the ones taking up just one slot. They tap into a single 120-volt bus bar running down the center of the panel. These handle your 15-amp and 20-amp daily loads, like overhead lights, bedroom outlets, your Wi-Fi router.
Exactly. And then you have the double pole breakers. They occupy two slots because they're physically connecting to two separate 120-volt bus bars simultaneously.
Which means they deliver double the power.
Right. They deliver 240 volts of pressure to your heavy-duty dedicated appliances. We're talking the electric oven, the central air compressor, the clothes dryer. You will see these rated much higher, at 30, 40, 50, or even 60 amps.
Okay, this brings us back to the hairdryer scenario I mentioned earlier. If you have a bathroom and a hallway sharing a 20-amp single-pole circuit, and running a hairdryer alongside a microwave consistently trips a breaker, the temptation is strong.
Oh, I see it all the time.
I mean, if my 20-amp breaker keeps tripping, why shouldn't I just pop down to the hardware store, grab a 30-amp breaker, and swap it out so it stops tripping? Problem solved, right?
If we connect this to the bigger picture, you'll see why that is incredibly dangerous. The breaker is a safety valve, not a bottleneck. Inside that breaker casing is a bimetallic strip.
A bimetallic strip, so two different metals.
Exactly. Two different metals bonded together, and each has a completely different rate of thermal expansion. As electrical current flows through the strip, it naturally generates heat. The 20-amp breaker is precisely calibrated so that if the current exceeds 20 amps, the heat causes one metal in the strip to expand faster than the other. This forces the strip to physically bend.
Wait, so it physically deforms from the heat generated by the overload?
Exactly. It bends until it eventually triggers a spring-loaded mechanism that snaps the connection open. That's the click you hear when it trips.
Wow, so the breaker doesn't just digitally know there are too many amps. It's a physical reaction to heat.
Yes, and that 20-amp calibration is purposefully matched to the physical gauge or the thickness of the copper wire hidden inside your walls. That wire is only rated to handle 20 amps safely.
So if you put a bigger breaker in
If you swap in a 30-amp breaker, you require significantly more heat to bend that bimetallic strip. Now, when your hairdryer and microwave pull 26 amps together, the 30-amp breaker stays cool and engaged. It doesn't trip.
But the wires in the wall are only rated for 20 amps.
Exactly. The 20-amp wire in the wall is experiencing what we call I²R heating. It literally begins to bake inside your drywall. The insulation melts, and the structural lumber around it ignites. The breaker is a thermal limit switch, not a performance upgrade.
Which introduces the core mathematical safety buffer that professionals use when calculating loads. The thermal physics we just discussed leads directly into what's called the 80% rule.
Yes, a vital rule. The National Electrical Code requires that continuous loads do not exceed 80% of a circuit's rated capacity.
And the continuous load is anything running for a long time.
Specifically, it's defined as any electrical draw running for 3 hours or longer without interruption. So an EV charger, a space heater, or like a dedicated server rack, those are all continuous loads.
So if you have a 20 amp circuit, 80% of that is 16 amps. Usually pull 16 amps continuously. It's like the red line on your car's tachometer.
Oh, that's a good way to look at it.
Right. Just because the engine can hit 6,000 RPMs and the numbers are printed right there on the dash doesn't mean you should drive on the highway like that all day. The thermal buildup will destroy the motor. You need a buffer.
Exactly. That 20% margin is the headroom that prevents the bimetallic strip and the wall wiring from slowly degrading under chronic thermal stress.
It gives the system room to breathe.
Yes, and it also provides the necessary slack for inrush current. Like when a refrigerator compressor kicks on, it requires a massive, instantaneous spike of energy just to overcome the resting inertia of the motor.
Oh, I see. So the 80% continuous limit ensures there is enough temporary capacity to handle that motor starting without crossing the thermal trip threshold.
You got it. But to apply the 80% rule, you actually have to know exactly what is running on a given circuit. You have to know your loads.
And that requires an accurate label chart on the inside of the panel door. But from my experience, those charts are rarely helpful. Like they are often faded out, completely blank, or just vaguely labeled with a single word like plugs.
Oh, I know. A vague label chart is completely useless in an emergency, and it makes calculating capacity incredibly difficult.
So what's the best way to fix a bad chart?
The proper way is to map it manually. You systematically power on a noticeable load in every room, like a lamp, a radio, or a fan. Then you manually actuate each single pole breaker into the off position one by one and trace the dead circuit.
And when you write it down, you don't just write kitchen right. You map it down to the exact zone, like kitchen outlets island or living room east wall. You really want to document the precise infrastructure.
Exactly. Taking an hour on a weekend to properly map your infrastructure eliminates all that catastrophic guesswork when, say, a pipe bursts and you need to isolate a zone quickly.
Oh, I bet.
Yeah.
And it probably saves a lot of money, too.
Oh, it drastically reduces the billable hours if an electrician needs to come out and troubleshoot a specific room. They don't have to spend an hour just figuring out what switch does what.
Here's where it gets really interesting, though. When you are looking closely at that label chart, you might realize your panel is a legacy model. We are talking about hardware that is 40 or 50 years old.
Right, which completely changes things.
Yeah, the standards have evolved, and corporate acquisitions have completely shifted the replacement market over the decades. The Copperfield Electric Guides detail the specific case of old Westinghouse panels.
Westinghouse panels were incredibly common back in the day, but the company's electrical distribution division was actually acquired by Eaton decades ago.
Okay, so if I have an old Westinghouse panel and a breaker breaks,
If a homeowner needs a new breaker for a 40-year-old Westinghouse panel, they cannot just buy a random breaker that happens to fit the slot. Eaton's Type BR breakers are the officially listed Underwriters Laboratories approved replacements for those specific legacy panels.
wow, because I think a lot of people just assume if it clicks in, it works. The physical fit is deeply misleading. Just because a breaker from brand X snaps onto the bus bar of a panel from brand Y does not mean it is mechanically sound.
Not at all. The tolerances in electrical panels are measured in fractions of a millimeter. Every panel is rigorously tested by Underwriters Laboratories using specific breaker clip designs to ensure maximum surface contact with the bus bar.
So if you use the wrong brand,
If you use an unlisted breaker, which the industry sometimes calls an alien breaker, the clip might feel tight, but the microscopic tolerance mismatch creates a poor connection point.
and a poor connection point creates electrical resistance.
Right. Resistance generates heat, and more dangerously, it causes microarcing. Tiny, continuous arcs of electricity jump across the imperfect connection. Over time, this microarcing pits the metal, carbonizes the surrounding material, and degrades the bus bar until the connection reaches a thermal runaway state and literally catches fire inside the panel.
Just from using a different brand of breaker. That is insane. And furthermore, installing an unlisted breaker fundamentally voids the UL listing of the entire panel.
Yes, it does.
Which means if that microarcing causes a fire, the insurance adjuster will come out, inspect the charred panel, photograph the unlisted breaker, and deny your claim outright because the hardware was modified outside of its engineered safety specifications.
Yeah, it is an incredibly high price to pay just for saving $15 on a generic replacement part at the hardware store.
So what does this all mean? I think the DIY line is drawn firmly at observation and documentation. Mapping labels and understanding your limits is critical, but the moment you encounter micro-arcing, scorch marks, buzzing, or you need to evaluate if your legacy panel can handle a continuous load upgrade, the intervention strictly requires a licensed professional.
Without a doubt.
And that is precisely where Copperfield Electric's infrastructure steps in. They are a family-owned, fully licensed, bonded, and insured operation, providing 247 emergency electrical services across the entirety of Orange County.
And, that 2047 aspect is not just a marketing point. It is an infrastructural necessity. The thermal runaway from a loose lug or microarcing does not adhere to normal business hours.
Right, wires don't care if it's 3 a.m.
Exactly. Catastrophic failures frequently occur under peak continuous load at extreme hours. Having an immediate professional response team guarantees that an overheating panel doesn't escalate into a structural fire while you're asleep.
And they cover a massive operational grid. Their service area stretches through Irvine, Anaheim, Santa Ana, Costa Mesa, Newport Beach, Laguna Beach, Mission Viejo, Huntington Beach, Orange, Fullerton, and Tustin. If you are in that grid, they are your primary resource.
They really do cover a huge area.
Yeah. Let's say you are in Anaheim, looking to convert your garage into an accessory dwelling unit, an ADU. You can't just run heavy new circuits off a maxed-out 100-amp legacy panel. Copperfield Electric handles comprehensive panel upgrades, taking you from 100 amps up to a modern 200-amp service.
They do it all.
They design the new construction wiring, handle the load calculations for dedicated EV chargers, manage complex lighting installations, and they even conduct full home safety outlet maintenance.
This raises an important question for anyone listening. When was the last time you actually evaluated the operational health of your home's main panel?
Probably never for most people.
Right. Copperfield Electric operates on the proven methodology that preventative troubleshooting is significantly cheaper than emergency reconstruction. Bringing a professional in to secure loose connections, verify breaker listings, and assess your thermal loads prevents the failure way before the bimetallic strips are forced to trip.
It's just smart, strategic maintenance for your property. So if you need a comprehensive panel assessment, or you're planning a capacity upgrade for an EV, or simply have a breaker that keeps detecting a thermal overload, you can engage Copperfield Electric at 626-622-9694 or 949-806-3807.
Highly recommend giving them a call.
They offer a streamlined online booking platform, and they maintain a 100% satisfaction guarantee with transparent, honest, competitive pricing. That contact again is 626-622-9694 or 949-806-3807.
Understanding your home's capacity isn't just about reading numbers on a switch. It is about respecting the physical forces contained within that metal box. Knowing how to safely observe those forces and knowing exactly who to call when the engineering requires intervention is the absolute foundation of property safety.
Beautifully said. And as we wrap up this deep dive, I want to leave you with a mechanical reality to really think about. The next time you walk into your kitchen and turn on the electric oven or plug your car in at the end of the day, visualize the unseen journey of that energy.
It is truly a marvel.
It is. Power traveling miles from the utility grid, pushing through the heavy 200-amp main shutoff in your garage, splitting across the dual bus bars, navigating the precise thermal physics of the 80% continuous load rule, and safely clearing those bimetallic thermal limiters inside your wall, all just to deliver exact sustained energy right to your fingertips.
It is a stunning feat of localized engineering.
It really is. So take 10 minutes this week. Just go to your garage or hallway, look at your panel from a safe angle, check the main service amps, and see if your label chart actually reflects the reality of your infrastructure. Understand the mechanics of your own home. Thank you for joining us for this deep dive. Stay safe, stay curious, and we will catch you on the next one.